You know, AI image classification is pretty much everywhere these days. It's in your phone's photo app, it's in cutting-edge medical diagnostics, and it recognizes images with almost superhuman accuracy. But what if these incredibly powerful systems have some serious hidden flaws? Well, today, we're going to peel back the layers and find out exactly what they are.
So, at the core of all this modern AI vision, you've got something called a convolutional neural network, or a CNN. Think of it as the AI's visual cortex. It takes an image, like this handwritten 3, and it just breaks it down layer by layer. The first few layers, they see really simple things, like edges and curves. But as you go deeper, the network starts piecing those bits together into more complex patterns. Until, bang, it classifies the whole image. This is literally how an AI learns to see.
Okay, but here's the real kicker. What if, during this whole complex learning process, the AI starts picking up on the wrong signals? What if it's not truly understanding the image, but just finding these clever little shortcuts that completely fall apart when you show it something new in the real world? This is where things get really, really interesting.
And look, this isn't just some theory. Recent research is actually suggesting that some of the progress we thought AI was making might just be an illusion. These hidden issues are inflating the numbers, making the models look better than they are. So that's what we're going to do today. We're going to put on our detective hats and investigate 3 of these major hidden flaws.
All right, our first case file is what I like to call the rote memorizer. Just imagine a student who crams for a big test just by memorizing every single word in the textbook. They'll probably ace the practice quiz, right? But then, on the final exam, the questions are slightly different and they totally bomb it. Why? Because they never actually learned the concepts. This is exactly what can happen to an AI.
And in the world of machine learning, this has a name: overfitting. The model gets so good at its training data, it learns every little detail, every bit of noise, that it just can't generalize to new information. It's essentially learned the training photos by heart, but it has no real idea what a cat or a dog actually is. And that's the key here. Memorization is not intelligence.
See, what you want is good generalization, where the model does a great job on both the data it's seen and brand new data it's never seen before. Overfitting, that's the trap. You get this amazing, exceptional performance during training that just plummets the second you give it a fresh data set. So, how on earth do we fix this?
Well, we fix it with some creative teaching, or what engineers call regularization. These are basically clever mathematical rules you add during training that stop the model from getting way too complex. They kind of introduce these little challenges that force the model to learn in a much more robust way, instead of just memorizing the answers.
Probably one of the coolest and most powerful tricks in the book is data augmentation. Instead of just showing the model the same exact pictures over and over again, we create a bunch of slightly altered versions. We might flip them, rotate them, maybe change the colors a bit. This teaches the model to focus on what's essential about an object, not just the random, superficial details of one specific photo.
And it gets even wilder than that. On the left, you see something called random erasing, where we just black out a piece of the image. This forces the model to make a decision based on only partial information. And on the right, cut mix. This is my favorite. It literally pastes a chunk of one image onto another, and then tells the model, hey, this new image is like 70% car and 30% helmet. It sounds absolutely crazy, I know, but it's an incredibly effective way to stop that memorization dead in its tracks. And believe me, the toolkit does not stop there. You've got dropout, which is kind of like having random members of your team call in sick, which forces everyone else to step up and learn more robustly. Then there's early stopping, which is basically like ending a study session right when you realize you're just rereading stuff without actually learning anything new. It's all about keeping the model on its toes.
Okay, so what if the model isn't just a bad student who memorizes? What if it's an actual cheater? This brings us to our second case file, the cheater. This is a student who somehow got a copy of the final exam before the test. Yeah, they got a perfect score, but that score is totally meaningless because it doesn't reflect any real knowledge at all. This, my friends, is called data leakage, and it is a huge problem. It breaks the #1 fundamental rule of machine learning. You never, ever evaluate your model on data that it saw during training. When that happens, your performance metrics are basically fake, and they give you zero clue as to how that model is going to perform out in the real world. So this leakage can actually show up in a few different ways. It can happen within a single data set, that's intra-data set, or it can happen between different data sets. The degree matters too. Hard leakage is the really bad one, where the exact same image is somehow in both your training and your test sets. Soft leakage is a little sneakier. It involves near identical images, like say a slightly cropped version of the same photo.
All right, so we've got our model to stop memorizing and stop cheating. But what if the problem isn't the student at all? What if the textbook itself is just wrong? This brings us to our final case, and it's probably the most dangerous of them all, the biased learner. This model isn't doing anything wrong on purpose, but it's learning from a curriculum that is fundamentally flawed and prejudiced. It's learning all the wrong lessons, and that leads to really unfair outcomes.
Let me give you a perfect and kind of scary real-world example. A while back, a model was built to spot COVID-19 in X-rays, but it learned a really dangerous shortcut. See, the negative examples, the healthy ones, often came from a dataset of pediatric pneumonia X-rays, which were frequently marked with the letter R. So the model didn't learn how to read the X-ray, it just learned to look for the letter R to decide if a patient was healthy. This is a textbook case of the model learning a false correlation from a biased dataset.
And that is algorithmic bias in a nutshell. The AI itself isn't malicious or evil. It's just learning from data that reflects our own societal biases or, just flawed ways of collecting information. And that bias gets baked right into the model's decision-making process. The bottom line is this: a model is only as fair as the data you train it on.
A really common way this bias sneaks in is through something called class imbalance. Imagine you're building a model to detect a very rare disease. If 99% of your training data is from healthy patients, the model can get 99% accuracy just by always predicting healthy. It looks fantastic on paper, but it's completely useless in practice because it never actually learns how to spot the rare cases that matter.
Okay, so after all that, you might be thinking, this is all doom and gloom. But how do we actually build better, fairer, more reliable AI? Well, the good news is that the path to fairness is one of the most active and important areas of AI research today, and it's absolutely packed with clever solutions. Well, to fight bias, engineers actually have this amazing toolkit. Things like reweighting, which basically tells the model, hey, pay extra attention to these rare examples. We've already talked about data augmentation, which can create more examples of underrepresented groups. And then there's transfer learning, which is like giving the model an unbiased foundational education on a fair dataset before it ever tackles a more specific and potentially biased task. And this chart right here, this shows that process in action. Engineers are tracking a fairness metric, you can see it on the vertical axis, and each of those colored lines represents a different technique they're trying out. The goal is to get that line down to 0, which would mean a perfectly fair outcome. You're literally watching them experiment and tweak things to get the model to unlearn its biases.
And what research shows over and over again is that there's no single magic wand here. The best, most robust, and fairest models come from thoughtfully combining these different strategies. It has to be a multi-pronged attack, right? Because each tool fixes a slightly different part of the problem. Reweighting handles imbalanced data, augmentation adds variety, and transfer learning gives you that solid, unbiased foundation to start with.
So when you boil it all down, it really comes to this. These powerful AI models, they're basically mirrors. They just reflect the data we feed them, with all of its flaws, all of its blind spots, and all of its hidden biases. The great challenge for us then isn't just about building more powerful algorithms. It's about being more careful, more thoughtful, and more deliberate about the data we use to train them. The question we really have to ask ourselves is, how do we make sure that mirror reflects the best of who we are and who we want to be?